Hi there, and thank you for joining this special on-demand webinar with Force and Tektronix on spectrum analyzers versus oscilloscopes. Before we get started, I would just like to say that you're free and encouraged to share the webinar with anyone that you think that might be interested. Our guest speaker for today will be taking questions. Please comment below or email marketing@testforce.com. We will supply everyone that registered to the webinar or watches the webinar with all the questions and the answers. Without further ado, I would like to introduce our special guest speaker, Keith Tinsley, application engineer from Tektronix. He is an expert in RF communications and digital signal processing. So let's jump right into the topic.
Thank you. Thank you very much for that introduction. It's my pleasure to join you today to talk about spectrum analyzers versus oscilloscope. This is an age-old question that a lot of our customers, as well as our sales force, have wanting to gain more understanding and understanding the different trade space that's associated with this in order to choose whether a spectrum analyzer or an oscilloscope is best for the application that it needs to be used for. So without further ado, let's talk about what we're going to cover today. We could talk about length, about spectrum analyzers, but I really want to give them both equal weighting here, because depending on the application or depending on what the problem is to be investigated, there are certain advantages in using one versus the other. So specifically, when it comes to looking at sharp edges or time domain signals, the oscilloscope has traditionally always been the instrument of choice. However, in order to capture, and we'll see later in the slides why a large bandwidth is needed to be captured, in order to create a sampler that runs fast enough to capture a large amount of bandwidth, there are certain artifacts that you have to deal with in order to have that capability. So engineering is all about trades, and when it comes to these two domains as related to products, spectrum analyzer and oscilloscopes, the story is similar. So most of our customers are falling into the range of radio frequency communications and markets. These span 5G and 6G, as well as some of our military and government users, as well as university researchers are looking primarily at 5G applications, whether that network is open to the public or that network is closed for private communications. And two main areas that are of importance as well as popular design right now are in the areas of MIMO, which are multiple input, multiple output systems, which really is a acronym that's used to describe multiple transmitters that can be received by multiple receivers, and that information can be collected as well as processed across all those antennas, which we call communication or spatial communication. And all that information can be used to compile and weight across them in order to improve performance, or individually assessed in order to maximize throughput. Again, another trade space. And then also, a lot of our customers are interested in beamforming. And what that actually is the steerability of these multiple transmitters or these multiple inputs for directive performance at a particular sector or vector or user, because they want to maximize or close the communication link, maximize performance, and give to people what they expect and what they're paying for with their service level agreements. So we at Tektronix are very aware that our customers, as well as our sales force, are going into meetings in which they have to communicate the value of choosing between a spectrum analyzer or choosing between a oscilloscope. But in the end, it all comes down to electromagnetics. This was the class that I can only speak for myself. I love attending this class. It's the basis of the work that I do today at Tektronix. But really, it's looking at the amplitude variation across time. It is the confluence of operation amplitude across time, as well as the amplitude or magnitude across frequency. Depending on whether or not this electromagnetic waveform is perturbed by some natural event, we could then talk about statistical operation or power spectral density across the frequency band. But in general, we're looking at how a particular frequency component translated into operation over time and how that amplitude is directly correlated to the power spectrum that's represented by that signal. So this, in essence, forms the definition of what an electromagnetic signal is, or wave equation. And we use that in order to determine how to design the oscilloscope in order to capture all these frequency components, or narrow in on a particular frequency component in order to understand its behavior or its support over a band of frequencies. So another trade space that we need to talk about is bandwidth versus spurious free dynamic range. So again, if we think about time domain signals, if you remember Fourier transforms or Fourier series, they're collections of a whole group of harmonics, which are compiled to represent that square waveform that you see in section B here. So in summary, section A is a collection of harmonics, which when we look at it in the time domain view in area B, that indeed is the square pulses that we are associated with. Now, it's very clear from the lower graph here, looking at the frequency domain. If we only looked at the support maybe a little bit around just the fundamental frequency, all those other components that we see, in this case up to 70 gigahertz, we would not capture, and that waveform in section B wouldn't look as sharp as it does now. And what that means for the designer is they won't be able to look at the rise and fall time accurately, and their measurements would be skewed. So this is a clear case in which you want to be able to capture a large amount of bandwidth in a very quick amount of time so that you could get all the harmonics that are associated with a particular pulse train to give you an idea of how well it's performing. Conversely, when we think about frequency domain measurements, or in this case, some particular time domain measurements, we have to think about spurious free dynamic range. And this gets into the earlier trade space that I talked about, where analog to digital converters. There are some artifacts that come in order for you to be able to process that large bandwidth effectively. And there are certain spurs that are created due to the architecture of the high-speed analog to digital converter, which, if you are measuring a signal that's close to those levels, are going to perturb your measurement. So in this case, if you're measuring a square pulse or a very strong RF signal in the frequency band with frequency support, you want to ensure that you operate within the spurious free dynamic range of the unit so that your measurements are accurate and that your distortion is minimal. So again, trade space between bandwidth, spurious free dynamic range, whether or not you measurement of time domain is important in terms of rise and fall time versus just looking at the random processes that are related to radio communications around a fixed support frequency if you're doing frequency domain measurements. So with respect to time domain, the DPO 70KSX series provides you, customer, the ability to measure performance of waveforms and ascertain what is the rise and fall times, as well as delay or distortion across strong signal level values to make a determination how your unit under test is performing. As is mentioned here, the spurious free dynamic range is sufficient enough in order to measure strong signals, as well as there's more than enough bandwidth and memory to capture event durations that allow you to determine how your pulse waveform or your clock is performing over a particular amount of time. However, for RF communications, in the case of 5G, looking at a particular banded performance of operation, you're really interested in what is the electromagnetic signal that exists over that fixed band of support. In this case, the RSA 7100 Bravo series allows for deep assessment, a greater spurious free dynamic range, so that you can evaluate at very low signals how your electromagnetic signal from your unit under test is performing. So in this case, the engineer or the customer or the manufacturer really isn't interested in capturing all those fundamentals, so from DC all the way up to 70 gigahertz. They're really, again, looking at performance over a particular band of interest. And for the 7100 Bravo, this band could be as much as 800 megahertz, and then allow for event recording on the order of 2 hours. This is primarily used by a lot of our military customers, that want to have the ability to stop, stare at a particular band of support, gather data and process that data real time, or process that data post acquisition. Some terms to be aware of whenever we're talking about radio communication, or in some cases time domain, things are related in terms of log scale. What this actually is a mathematical instrument which allows you to relate the relative change of one event relative to the other. And so 0 dB in this case is there's a 1-to-1 relationship. On the order of 10 dB, we're looking at a 10-to-1 relationship, and 20 dB, it is 100 to 1, and so on and so forth. And this is related to the fact that the log function is used in order to relate the fundamental change between, in this case, power that's incident in time 1 versus power that's incident in time 2. So again, different equipment for different tasks and different measurement objectives. For an amplitude modulated signal, transient communication, the RSA 7100 Bravo may in fact be the best instrument for use. If you could see here on the left, there are only really 3 fundamental frequency components that are of most interest, which fully describe the rate of change of the electromagnetic signal that's under observation. With respect to time domain and use of the DPO 70KSX, in this case for a periodic waveform, each one of those frequency components, which are represented here by this sine x over x pattern, are critical. These are critical in order to describe the rise and fall time and overall shape, the squaring of this signal, which needs to be analyzed in the case, say, of a clock, to make sure that you could trigger the event in the amount of time that's needed in order to ensure that precision and timing is kept within the instrument under test. Some features of the DPO which help to improve the engineer or customer in order of evaluating the performance are vertical averaging of multiple, or fast frame averaging, which is essentially vertical averaging of multiple frame sets. So each one of these ensembles are collected, say in frame 1, frame 2, and frame 3. And these are the characteristics, the behavior of the clock over time. Because all instruments contain an inherent amount of noise due to its operation on the atomic level as the electrons move through the lattice and they get perturbed. All that translates into noise, which will eventually show up as jitter. This fast frame averaging allows for a collection of that performance over multiple ensembles to give you an assessment of what the average performance is at each one of those time instances in order to give more confidence that indeed the unit under test is meeting the desired performance or reliability. So again, with respect to frequency communications, why look at the RSA 7100? It's typically for myself, looking at radio communication, it's dynamic range, which is directly correlated to spurious free dynamic range. What is the lowest signal that I could detect, and what is the strongest signal that I could detect? And the lowest being a function of, again, that intrinsic noise, which is inherent to the electronic device. How quiet can it be? And the strong signal related to what we call the 1 dB compression point, which is correlated to distortion in this case. It is the level in which you drive the instrument hard enough that it starts to, for lack of a better term, feed on itself, and spurs start to increase, which again, getting back to our definition of spurious-free dynamic range, impacts that. So with an instrument, in the case of the 7100, with a very strong dynamic range, the analysis of band-supported RF communications can be done effectively, as in the case here with 5G modulation. Now, these characteristic eye patterns that you see here over in the bottom right are related to decision points on the I and Q axes. These are orthogonal signaling pairs, which form the basis set for communication of this data. So clearly, there are 4 decision regions here, and the user can disperse the data across these 4 decision regions. And because of the strong dynamic range, in this case of the measurement equipment, analysis of the transmitter and its performance can be done effectively. So if there is distortion, if that decision region becomes blurred with the other one, it is due to some incident in the transmitter or some item that needs to be investigated. In short, the equipment needs to be better than the environment in which you're transmitting in to make a determination that indeed the unit under test can perform well in the environment that it's going to be subjected to. So when we talk about time and frequency, it's really a linkage or a dichotomy between the both of them. And Tektronix instruments perform this to a T. What we have in both the DPO as well as in our time domain or time qualified triggers in the RSA products is allowing for measurement and marking of instances in time and seeing exactly how those translate to their unique frequency components. It's something that we have been instilling and continue to improve in our time domain and frequency domain products, as well as looking to the future in terms of improving the range of performance for a lot of our Tektronix equipment. Those that currently extend to only 26 gigahertz, we are looking to invest in a disaggregate front-end module that allows for measurement of performance of signals up at 40 gigahertz and thereby extending the range of the 7100 Bravo. And with that extension to 40 gigahertz, the RSA 7100 allows or gives to the customer the ability of the DPX transform engine. And what this is a signal processing engine, lack of a for lack of a better term, that allows for processing of large amounts of signals, translating them into their unique frequency components per the fast Fourier transform algorithm, and thereby correlating them exactly to their instances in time. What the DPX engine does is up to 5.1 million transforms per second are used in order to characterize the behavior of the signal in the frequency domain, as well as correlating it to how it is evolving in the time domain. In this case, what we show here is a persistent display of RF performance. That's shown here at the bottom. Now, this is important for a lot of our RF customers who are looking for performance over a particular band of interest and looking for signals that may be hidden by a traditional swept analyzer, which is not moving at a rate fast enough in order to capture the signal that which may be aperiodically pulsing on. In this case, it may represent a jammer, or it may represent someone who means to do nefarious action to the target receiver. This performance of the DPX engine in the 7100 is a little different than the DPO series instruments. This is over a single channel, and it allows for a tighter correlation between time domain and frequency domain. In this case, as we show here in the time overview, allows for understanding of how the amplitude versus time changes and how that is correlated to particular frequency of events. You see over here on the left, there's a little bit of overshoot and ringing when the pulse turns on, and that indeed may translate to unwanted spectral contributions, which is shown here in the magenta line over in the other display. And again, currently now the 7100 series goes up to 26.5 gigahertz, but with the work that we're investing in for extending the range, indeed, we're looking to provide services to customers who want to operate up to 40 gigahertz. So when, in the other case, to sell the DPO as an RF spectrum analysis instrument really calls into question also making use of SignalVu PC on a scope. This is a great opportunity for Tektronix to break into the area of wideband communications, primarily at 60 gigahertz, because the instrument does a very good job of collecting signals from DC all the way up to 70 gig, and in some cases beyond. Looking at operation in the 802.11 alpha delta band, as well as various line of sight communications. Wideband military applications below 70 gigahertz, provided the appropriate gain structure is put in front of it, can be investigated with the DPO 70K series SX scope, as well as investigating spectral management for signals that occupy in and around 70 gigahertz. Some targeted customers maybe you may want to give some thought to, or Qualcomm and Broadcom, primarily using the scope as an instrument to evaluate beamforming alignment between multiple receivers and unique transmitters, as well as overall performance of independence associated with MIMO channels as collected by a unique 70K instruments. So again, depending on the application, may warrant a particular product, and depending on the phenomena to be measured, it may warrant whether or not a large amount of bandwidth is needed, or only investigation with strong dynamic range over an area of fixed spectral support may be indeed what you need, in which case the 7100 series RSA may be the best instrument for the job. So it's important when talking to future customers about RF, really to understand what's most important. Is it understanding the rise and fall time for a particular trigger that is used to turn a power amplifier on? And that power amplifier may indeed have some particular artifacts which may arise by pulsing or turning the instrument on. And you indeed want to understand how does the spectrum change as that instrument goes from that overshoot situation, settling to that steady state. Why? Because that may indeed affect the spectral mass performance and thereby make the transmitter not optimal for the band in which it's operating in. In that case, either a 7100 Bravo RSA instrument or a DPO 70XK instrument could do the job. There may be other uses that the customer may be looking at the performance of the transmitter as it relates to error vector magnitude. So again, we at Tektronix see a lot of work being done now and in the future as related to 5G and 6G. As you see here, there are bands that are being allocated in multiple areas across the world. And we see our customers wanting to have equipment that can efficiently measure the spectral performance in both and how it changes in both the time and frequency domain simultaneously, as well as looking at the performance of transmitters, or in other cases, looking at the performance of MIMO or beam steered systems now and in the future. So I want to thank everybody for taking the time today to listen to me speak about a subject that I'm very passionate about and that I love. If you do have questions, please submit your questions below or email marketing@testforce.com. The deadline is July 21st, 2021, and I look forward to speaking to everyone again. Thank you.